Welcome to the Deep Dive. You give us the sources, we give you the insights. Today, we're tackling something huge. Robert Oerter's The Theory of Almost Everything. It's his look at, well, the standard model of particle physics.
And that title, Almost Everything, it really isn't an exaggeration, is it? The source actually quotes Neil deGrasse Tyson on this.
Oh yeah, what does he say?
He calls the Standard Model a triumph of 20th century science that underpins nearly all we know about physical reality. I mean, that's big.
That sets the stage. So our mission today is to unpack why it gets that name. What makes it so powerful? What were the big ideas needed to build it?
And crucially, why almost everything? What's missing?
Right. But let's start with the elegance. You mentioned something before we started recording that just floored me.
Ah, yes. The parameters. Think about this. The Standard Model explains the fundamental structure of matter, all the forces except gravity. And the whole thing, the entire mathematical structure, is defined by just 18 numbers.
18. Just 18 constants
Yeah.
to, run the universe minus gravity.
Basically, yes. From how atoms hold together to how light works, it boils down to those 18 values.
That's kind of mind-bending. It suggests there's a real simplicity under all the complexity we see.
Exactly. That's the deep structure physicists are always hunting for.
Okay, let's ground this for the listener. When you say it governs daily life, what do you mean specifically?
Well, pretty much everything you experience that isn't gravity. Think about matter itself, the fact that things are solid.
Like this chair I'm sitting on.
Precisely. And light, radio waves, X-rays, all forms of electromagnetism, plus every chemical reaction. Cooking, breathing, your phone's battery.
So my own body functioning, the electricity in the walls, that's all standard model territory.
Fundamentally, yes. It comes down to electric and magnetic forces. The source really hammers this home. These forces are what hold atoms together, what stop your hand passing through the desk.
It's the electric force, basically, keeping things solid.
Exactly. Movement, digestion, even thinking involves electrical signals in your nerves. It's all governed by the rules the SM describes, particularly quantum electrodynamics, or QED, which we'll get into.
Okay, but that brings us straight to the elephant in the room, or maybe the planet under our feet. Gravity. It feels like the most dominant force, yet the SM just ignores it.
It seems paradoxical, doesn't it? But here's the thing. Gravity is unbelievably weak compared to the other forces.
Weaker. It holds planets in orbit.
Yes, but only because planets are huge and electrically neutral. Consider just two protons. The electrical repulsion between them is 10 times stronger than their gravitational attraction.
10 to the power 36. That's a 1 followed by 36 zeros.
It's an absurdly large number, a million times stronger.
So why do we notice gravity at all then?
Because large objects, like you, me, the Earth, they have vast numbers of protons and electrons, but the positive and negative charges cancel each other out almost perfectly, so that incredibly strong electric force just disappears on the large scale.
Ah, okay. So the net charge is near zero, canceling the big force, leaving only the tiny cumulative effect of gravity from all that mass.
Exactly. Gravity only dominates because it always adds up, it never cancels. But at the scale of fundamental particles where the SM operates, gravity is utterly negligible. You have to leave it out to get the theory right for that domain.
That makes sense. It clarifies the almost. Now, about the level of explanation, does the SM give us, an equation for a chair?
No, absolutely not. And that's a really important distinction. The source uses a great analogy, a computer.
Okay.
The Standard Model describes the fundamental circuitry, the protons, neutrons, electrons, photons, how they interact, the basic hardware components.
Right. The transistors and wires, so to speak.
Exactly. But it doesn't describe the complex structures built from that circuitry, like the operating system or the web browser or a video game, a chair or a biological cell or a thought. Those are higher level phenomena.
So chemistry, biology, neuroscience. Those are like the software running on the SM hardware.
That's a good way to put it. You need to understand the hardware, the SM, for a fundamental understanding. But describing the complex behavior requires these higher-level sciences. The SM provides the ultimate building blocks and rules, but not the blueprints for every complex structure.
Got it. Okay, so building this theory wasn't easy. It required some major shifts in thinking, right? Going back to the 19th century.
Absolutely. A key problem was this old idea of action at a distance. How does the sun heat the Earth across empty space? How does a compass needle know where north is?
It seems spooky if you think about it without feels.
Right. The solution was the field concept. Think of a barbecue. You smell the smoke, right? The source of the smell creates a smell field, and your nose detects the field right where you are.
So no spooky action, just a local interaction with the field.
Exactly. A charge creates an electric field everywhere in space, and another charge feels the field at its location. Problem solved.
And this field idea really took off with James Clerk Maxwell.
Oh, hugely. In 1865, he unified electricity and magnetism into one theory of electromagnetism. He showed that changes in these fields create waves.
And the speed calculation.
That was the stunner. He calculated the speed of these electromagnetic waves from his equations using purely electrical and magnetic measurements, and it came out as the speed of light.
So light is an electromagnetic wave. That's monumental.
It really is. And that discovery that the speed of light is fundamental directly leads into Einstein.
Special relativity.
Yeah.
Built on a simple but radical idea.
Just one postulate, really. The speed of light in a vacuum is the same for all observers, regardless of their motion.
Which sounds simple, but it completely messes with our intuition about space and time.
It has to. If the speed of light is constant, then distance and time cannot be absolute. They become relative, observer-dependent. They stretch and shrink to keep c-go constant for everyone. Space and time get woven together into space-time.
And the evidence for this isn't just theoretical. The time dilation effect.
Oh, it's measured constantly in particle accelerators. You take particles with very short known lifetimes, you accelerate them close to the speed of light.
And they live longer.
Way longer, thousands of times longer, exactly as predicted by relativity. Their internal clocks literally run slower relative to us. GPS systems even have to correct for these relativistic effects, both special and general, to work accurately.
Amazing. And linked to this is probably the most famous equation ever.
AUS MC22. Mass is energy. Energy is mass. There's two sides of the same coin.
Now, the conversion factor, 222 the speed of light squared, that tells you mass holds a huge amount of energy.
An unbelievable amount. The book gives a great example. Convert 1 grain of salt entirely to energy, and you could power a standard light bulb for about a year.
A year
Yeah.
from 1 grain of salt. Wow. Okay, that really drives home what mass is, just incredibly concentrated, slowed down energy.
Pretty much. And this equivalence also implies the cosmic speed limit. If you have mass, you can never reach the speed of light because your energy would become infinite.
While massless particles, like photons, must travel at $2.
Exactly. There's no middle ground.
Okay, one more foundational concept before we get to the quantum weirdness. Symmetry. This seems crucial. Emmy Noether's theorem.
Noether's theorem. It's one of the most beautiful and profound ideas in physics. She showed mathematically that for every continuous symmetry in the laws of physics, there must be a corresponding conserved quantity.
So symmetry isn't just about things looking nice, it forces things to be conserved.
Precisely. It takes conservation laws from being sort of empirical rules to being mathematical necessities.
Give me an example.
Okay, the laws of physics seem to be the same today as they were yesterday and as they will be tomorrow. That's time shift symmetry. Noether showed this symmetry requires energy to be conserved.
Wow. And what about moving things around?
If the laws are the same here as they are, say, on the moon, that's spatial shift symmetry, then momentum must be conserved.
So that's why in a car crash, the total oomph before equals the total oomph after, even if it's distributed differently.
Exactly. It explains why the wreckage generally continues in the direction the Mack truck was going, not the sedan. Momentum conservation, guaranteed by spatial symmetry. It's incredibly fundamental.
Fields, relativity, symmetry. Okay, now we combine them with quantum mechanics. This leads to quantum field theory, QFT.
Yes. Relativistic quantum field theory. It's the framework that underlies the Standard Model. It marries special relativity with quantum mechanics and the field concept. And here's a key shift. In QFT, fields themselves are quantized. They come in discrete chunks or particles.
So the distinction between particles and fields kind of dissolves.
In a way, yes. Particles are excitations or chunks of their underlying fields. The electron field gets excited and boom, you have an electron. The photon field gets excited, you get a photon.
And the first really successful QFT was QED, quantum electrodynamics.
Right. It describes the interactions of electrons, positrons, the electron's antiparticle, and photons. And its triumph is its absolutely stunning predictive accuracy.
This is the magnetic moment thing you mentioned earlier.
This is it. The electron behaves like a tiny magnet. An early equation by Dirac predicted its magnetic strength, but it was slightly off from experimental measurements.
Slightly off, but in physics, slightly off usually means something's missing.
Exactly. QED fixed it. The theory says an electron isn't just a bare particle. It's surrounded by a buzzing, frothing cloud of virtual particles.
Virtual particles, like ghosts popping in and out of existence.
Sort of. They're fluctuations of the quantum fields. They can briefly borrow energy from the vacuum, thanks to the uncertainty principle, exist for an incredibly short time, and then vanish. They affect the electron's properties.
And including these, ghost interactions,
Uh,
makes the prediction match.
Well, not perfectly, but to an astonishing degree. QED's prediction for the electron's magnetic moment matches the experimental value to about 1 part in a billion. It's arguably the most precisely verified prediction in all of science.
So this incredibly weird picture particles surrounded by fleeting ghosts, taking maybe virtual faster-than-light trips to the moon and back as part of their existence.
Yes, Feynman talked about calculating paths where electrons do absurd things like that.
That bizarre picture is what gives us this unbelievable accuracy.
It is. As Feynman famously said, QED describes nature as absurd from the point of view of common sense, and it agrees fully with experiment. We just have to accept that reality is that absurd at the fundamental level.
Okay, QED covers electromagnetism, but then physicists started finding tons of other particles.
Yeah.
The subatomic zoo.
They did. Accelerators in the mid-20th century were churning out new particles weekly, it seemed. It was chaos until Murray Gell-Mann proposed the eightfold way to organize them, which led to the idea of quarks.
Quarks is the really fundamental things inside particles like protons and neutrons.
Exactly. Protons and neutrons, which are called baryons, aren't fundamental. They're made of 3 quarks each. A proton is 2 up quarks and 1 down quark. A neutron is 1 up and 2 downs.
So what holds the quarks together inside the proton? Another force.
Yes, the strong nuclear force, described by quantum chromodynamics, or QCD. It's analogous to QED, but for quarks.
Analogous, but different, right. The force carrier is different.
Very different. In QED, the force carrier is the photon, which is electrically neutral. In QCD, the force carriers are called gluons, and crucially, gluons themselves carry the charge of the strong force.
What's the strong force charge called?
It's whimsically called color charge. Quarks come in 3 colors, red, green, or blue, and antiquarks have anticolors. Gluons carry combinations of color and anticolor.
And the fact that gluons carry color themselves makes the strong force behave weirdly.
Utterly weirdly, in 2 key ways. First, asymptotic freedom. Unlike electromagnetism, which gets stronger as you get closer, the strong force gets weaker at very short distances or high energies.
Weaker up close, that seems backwards.
It does, but it means if you hit quarks really hard, they behave almost like free particles inside the proton or neutron. This was experimentally confirmed and was crucial for validating QCD.
Okay, that's weird. What's the second weird thing?
Color confinement. Because gluons carry color, the force field doesn't spread out like electromagnetism. It seems to form flux tubes, like rubber bands, between quarks. And if you try to pull quarks apart...
The rubber band gets tighter.
Exactly. The force gets stronger the farther apart you pull them. It requires infinite energy to pull a single quark completely free from others.
Infinite energy, so you can never actually isolate a quark.
Never. That's why we only ever observe quarks bound together in color-neutral combinations. Either 3 quarks, baryons like protons, or a quark-antiquark pair, mesons. Nature confines color.
Wow. Okay, so we have QED for electromagnetism, QCD for the strong force.
Oh, yeah?
They're unified with the weak force too, right? The electroweak theory.
Yes, that was another major triumph. Unifying electromagnetism and the weak force, which is responsible for certain types of radioactivity, like beta decay.
And that unification involves something called spontaneous symmetry breaking. That sounds contradictory. Breaking symmetry helps.
Yes. It does. It's a fascinating mechanism. At very high energies, the electromagnetic and weak forces are expected to be unified, perfectly symmetrical, mediated by massless force carriers.
But that's not what we see at low energies. The weak force carriers, the WZ bosons, are incredibly massive, while the photon is massless.
Right. Spontaneous symmetry breaking provides a way for the underlying laws to possess a symmetry that the actual state of the universe doesn't fully exhibit at low energies. The Higgs field is involved here. As the universe cooled, interacting with the Higgs field broke the electroweak symmetry.
Giving mass to the W and Z particles, but leaving the photon massless.
Exactly. It's like a pencil balanced perfectly on its tip, symmetrical state, which inevitably falls over into a less symmetrical but stable state. The symmetry is still there in the underlying physics, but it's hidden in the outcome.
Amazing. So this beautifully constructed standard model, QED, QCD, electroweak theory, it works incredibly well. But it's still almost everything. Where does it fall short? What are the confirmed problems?
Well, The first concrete crack in the SM's perfection came from neutrinos. The original model requires them to be massless.
But they aren't, are they?
Nope. Experiments have shown that neutrinos oscillate, they change from one type or flavor to another as they travel. And quantum mechanics dictates that for this oscillation to happen, at least one type of neutrino must have mass. It might be tiny, but it's not zero.
So that's definitive proof of physics beyond the standard model.
It is. It's often called the first real experimental evidence demanding something new. We need to extend the model to accommodate neutrino mass.
What else? Are there more aesthetic problems? Things the model just doesn't explain.
Oh, definitely. Big ones. For instance, why are there three generations or families of fundamental particles, quarks and leptons? The electron has heavier cousins, the muon and the tau. The up quark has heavier versions, the charm and top quarks. Why three sets? Why not one or five? The SM doesn't say.
And those 18 parameters we started with.
Right. Why do they have the specific values they do? Why is the top quark, for example, something like 45,000 times heavier than the up quark? The masses are all over the place. The SM uses these numbers but doesn't explain their origin. It feels arbitrary, like we found the machine, but not the designer's notes.
Okay, so missing neutrino mass, unexplained families and parameters. What about the really big picture, the universe itself?
That's where the SM hits major walls. All the particles and forces described by the standard model only make up about 5% of the total mass and energy content of the universe.
Only 5%, what's the rest?
About 25% seems to be dark matter. We know it's there from its gravitational effects on galaxies, but it doesn't interact via electromagnetism, so it's dark, and it cannot be made of any standard model particle. That's something totally new.
And the other 70%?
That's even more mysterious. Dark energy. It's some kind of energy inherent in space itself that's causing the expansion of the universe to accelerate. We have absolutely no explanation for it within the SM.
Wow. So 95% of the universe is unaccounted for by our best theory of fundamental particles and forces.
Pretty much. It highlights how much we still don't know.
And finally, the original omission is still there.
Gravity. It remains stubbornly separate. General relativity describes gravity beautifully on large scales, but it's fundamentally incompatible with quantum mechanics. Merging them into a theory of quantum gravity is perhaps the biggest challenge in theoretical physics today. The SM offers no help there.
So the standard model is this incredible achievement built on profound ideas like fields, relativity, symmetry, quantum mechanics, yet it's clearly incomplete.
Absolutely. A stunning success, but definitely not the final word. Which brings us maybe to a final thought, circling back to symmetry.
Yep.
We mentioned that QED and QCD are types of theories called gauge theories or Yang-Mills theories. There's this deep principle behind them, sometimes summarized as ignorance is strength.
Ignorance is strength. How does that work in physics? Sounds odd.
It relates to symmetry. Imagine you couldn't tell the absolute value of electric charge locally. What if the definition of charge could be slightly different here compared to over there without changing the physics? The theory demands a way to compensate for this ignorance.
And that compensation requires?
It requires the existence of a mediating field, a force carrier that connects these different points and ensures the overall physics stays consistent despite our local ignorance. For electromagnetism, that mediator is the photon. For the strong force, it's the gluons.
So the existence of light itself, the photon, is a mathematical necessity arising from a fundamental symmetry related to charge.
In this view, yes. The forces, the very stuff that holds the world together and allows interaction, might exist because of these deep symmetries, because of what we fundamentally cannot know absolutely at every point in space and time.
That's a powerful thought. That the structure of reality, the forces and particles, might be the universe's way of enforcing its own underlying symmetries.
It suggests that understanding these fundamental symmetries is the key to understanding why the world is the way it is, even its most bizarre quantum features. It's a profound link between abstract mathematical principles and concrete physical existence.
Something profound to think about indeed. Thank you for joining us on this deep dive into the theory of almost everything.